Assignment 10, problem 6. We've seen this situation before. So current 1 is going up, and by right-hand rule number 2, looking at it from above, the field is counterclockwise. So this is I1. This is the field due to it. Wire 2, with a current in the same direction, is in the influence, lies in the field of B1. And so if we look down on that situation with the currents going up, here's wire 1 with current 1, here's wire 2 with current 2, here's B1, and so using right-hand rule number 1 with our finger in the direction of the current, which is coming out of the page, and the other fingers in the direction of the field, which is going up, our thumb points to the left. So F2 is the force on this wire, so you can see it's going to move toward the wire. And if we reverse the process, wire 1 is in the field of wire 2, and if we went through that in the same way, we'd see that the force on wire 2 has to be towards, the force on wire 1 has to be towards wire 2, so they attract each other. Okay, problem 7, we have 3 wires with current going into the screen, and we're told that they're all equal, and then there's a point, and the 3 wires in the point form a square of side S, and we want to find the magnitude and the direction of each field vector due to each of the wires at this point. So by right-hand rule number 2 for a straight wire, the field are circles going clockwise. So B1, the field due to wire 1, is going to be down. And B3, due to wire 3, is going to be to the left. And B2, due to wire 2, is going to be between them. And I'm going to draw it shorter because that wire is further away, so that field is weaker. If you get confused about how to get the field due to a wire, like in this situation, just draw a line from the wire to the point, and the field has to be perpendicular to that, right? Because it's a circle, that's a radius line. And so the field would have to be perpendicular to that. So we know the equation for the field due to a wire. It's B equals mu naught I over 2 pi, whatever the distance is. And in this case, the distance from wire 1 to the point is S. So it's mu naught I over 2 pi S. And so that's 1/2 mu naught I pi S. That's what we're finding it in terms of, and so it's just 0.5, and B3 is also a distance S, and it's going to be the same, and B2 is going to be at this angle, 45 degrees below the negative x-axis, but this distance is what? So we see this so often, you should just, I hope you know it by now, if this is S and this is S, this is the square root of 2S, right? If this is 1 and this is 1, this is the square root of 2. So the distance is the square root of 2S, so we have B2 equals mu naught I over 2 pi square root of 2S. So if we take out the coefficient, it's going to be 1 over 2 square root 2, which is 0.35355. It rounds to 3 significant figures to 0.354. And it asks for the angle, so of course the angle to B1 is going to be 270 degrees, and the angle to B3 is going to be 180 degrees, and this is going to be 225 degrees, as we're instructed to measure counterclockwise from the x-axis. Okay, now we have to add those three vectors together. So B1 has only a y component, B3 has only an x component, and B2 has an x component, which we have to add to this because they're in the same direction, and the same x component here, which we have to add to that because that's in the same direction. And so the final vector is going to be the square root of the square of both of those, and the direction will be in the same direction, 225 degrees. Let's see, so let's just get that component for you. So the magnitude, this is the coefficient of the magnitude of that shorter vector, right? And to get its x and y components, since it's at 45 degrees to the two negative axes, it's going to be the sine and cosine of 45, which is the square root of 2 over 2. So multiply this number by sine or cosine of 45, or the square root of 2 over 2, and what do you get? Surprise, it turns out to be 1/4. Oh, that makes sense, because if this is the coefficient, and we multiplied this by the square root of 2 over 2, then the square root of 2 would cancel, and it would end up being 1/4. So we could have done that without the calculator. So the coefficient is 1/4, and we're adding that to a coefficient of 0.5. So the coefficient for this vector is 0.75, and this one, the total of the two components, is going to be 0.75. And if we square those and take the square root, we will get that, right? So that's the coefficient of the final vector, and you can see the sum of those two vectors, this vector and this vector, this is getting to be a mess, would be a vector of unit 1.06 in that direction. Okay, done with that one. Actually, we're not done. There's another part where the currents aren't equal. So you're going to end up, in that case, you're going to end up with an I1 this way, and an I3, which is 50% bigger because the current's 50% bigger that way, and then an I2 in this direction where the current is bigger but the distance is greater, so I'm not quite sure how that's going to be. But now you have to, find the magnitude of these two, find the components of the middle one, and then add those components, and then just do the same math that we just did. So you just have to work through the details. I'm going to leave that up to you. Once again, this is, okay, number 8. Once again, use the right-hand rule. Let's start with A. Right-hand rule number 2. Curl your fingers. BA goes that way. BB goes that way, right? Perpendicular to the radius vector, tangent to the circle. C goes in the same direction as BB, so that's BC, BB, and BA and BD are the same. So all 4 of those vectors are going to have the same magnitude, right? They're going to be mu naught I over 2 pi times that distance. And what is that distance? If the diagonal is the square root of 2, then this distance is half of it, the square root of 2 over 2 s. The 2's are going to cancel. And so each vector is mu naught I pi over s 1 over the square root of 2, which is the same as the square root of 2 over 2, or 0.707. So the magnitude of all those vectors are the same. And the total electric field, B total, is just going to be 4 times the y component of any one of them, right? Because there's two x components this way, two x components this way, they cancel, but there's 4 y components down. And the y component is just going to be this magnitude, right? The magnitude of 1 times 4. So if we multiply this by 4, we're going to get 4 over the square root of 2. Yep, 4 over the square root of 2, which is 2 times the square root of 2, or 2.828, 2.83 mu naught I over 2 pi. A lot of symmetry, so not too hard to do. In the second part, you're going to have to deal with currents that aren't equal. So, like before, you're going to have to get components that aren't equal and add them all up and get the result. Number 9 takes us back to this figure. And the first thing we want to find is B1. So B1 is going to be mu naught I over 2 pi A. And it asks for the direction, but notice that the direction is using this set of coordinates, x for figure A, y, and z out of the page. So you can see from the figure that the field is coming in and out of the page, coming out of the page, going around, going into the page. So where wire 2 is, this is heading into the page, so it's negative k hat. And the magnitude is just going to be, use the numbers that are given. So here's our equation for a wire. We're getting B1 at wire 2, so we have to use I1. And mu naught is 4 pi times 10 to the minus 7. Notice I put the units in Tesla meters per amp. This is amps. 2 pi, the distance, 2.4 millimeters, so that's 0.0024 meters. And then what we get is we get the meters canceling and the amps canceling, and we end up with Tesla, and this becomes 3,000 times 10 to the minus 7 Tesla, or 300 times 10 to the minus 6, or 300 microtesla in the direction negative k hat, or negative k. Okay, I'll let you finish the rest of 9. We'll jump ahead to 10. So we have a wire carrying current this way. It bends into a loop, and then it goes out this way. So the thing to recognize is you have basically a long straight wire, and a current loop. And we're asked to find the field at the center of the loop. And so there's an equation for that derived from the Biot-Savart law that says B for a loop is mu naught I over 2R. So no surprise, the field there is going to depend on the current and how big the loop is. If the loop is smaller, the field will be stronger. That makes sense. And the direction of that field due to the loop, we use right-hand rule number 3. Since the current is this way, it's going to go around clockwise. So the field at this point due to the loop is into the screen. But then we have the wire. And so we have to add to the loop B for a wire. And we certainly have used that a lot. Mu naught I over 2 pi A. So the total field will be the sum of these. Oh, we got to check the direction. We can only add them, they're vectors, right? So the wire, using right-hand rule number 2, pointing my thumb that way. Oh, luckily the field is in the same direction. The field is into the page. So they are in the same direction, so we can just add them. Oh, but wait, the A, right, the A, the 2 pi A, I use A or you could use R. It's the distance from the point to the wire, so that is the radius. So the A, the distance from the wire to the point, is the same as the radius of the circle. It's this distance here, the radius of the circle, or the distance from the wire to the point. So that's lucky. So all we got to do is multiply by pi over pi, right? I hope you know these algebra tricks. So now we have 2 pi r in the denominator, and we have mu naught I over pi r. But what's left is a 2 here, and there's a pi plus 1. Did you follow that? All right, the 2, we have pi r, mu naught I, but when we factor out the mu naught I, we're going to have pi plus 1 in the numerator and a 2 in the denominator. And so that coefficient is equal to 2.07 if you do calculate it. So that's the coefficient of this. And the direction, of course, we already said is negative k hat, into the screen, both by right-hand rule number 2 for the wire and right-hand rule number 3 for the loop. So number 11, we have a wire that bends and turns, so it's not a sharp 90-degree angle. The two wires are perpendicular to each other, but it bends in a curved circular path, and we want to find the field here. So think of this as 3 different pieces. See if you can see what the 3 different pieces are, and then we can use that to solve the problem. What are they? So one piece is a long straight wire, half of an infinitely long straight wire in that direction. then half of an infinite long straight wire in a different direction, right? If you imagined that this wire kept going, but it doesn't, it stops there. That makes it just half a wire because this point is right underneath that point where it starts curving, and the same way here. So we have 2 half wires, and if you use right-hand rule number 2, pointing your thumb in the direction of the current, you can see that the field due to the top half wire is this way. And luckily, if you use right-hand rule number 2 for the bottom part, the field is in the same direction. And then what's the other part between them? It's a quarter of a circle, right? This is a circle, and that's a quarter circle. So we have to add, and right-hand rule number 3, the current circulating counterclockwise. So the direction of the field for all 3 pieces is into the board, and so all we got to do is add half of mu naught I over 2 pi a, but a is the radius, right? The radius of the circle. That's all r, 2 pi r, plus another half for this wire. Well, why don't we just call it 1, 2 halves, plus the loop, which you know from the last problem is mu naught I over 2r, but it's only a quarter of a loop. So we have to add those 2 parts. I'm going to leave you to do that algebra, and also then use the numbers because the current is given as 7 amps and the radius is given as 12.4 millimeters. Remember, that's millimeters, 10 to the minus 3 meters. So I tried drawing this. We're given number 12. We're given an x, y, and z axis in this orientation. And the 2 wires are running parallel to the x-axis, going through the y-axis. And they were distance a from the x-axis as they run parallel to the x-axis. And then we're going to pick a point 2a up here, say, where we want to calculate the field. And so there's going to be 2 vectors. We'll call this wire 1 and this wire 2. And that's going to give us 2 vectors on the z-axis. But this is going to be hard to draw in 3 dimensions, so watch what I'm going to do. So to better visualize it, I've put the y-axis here, kind of as it was, but I've rotated the thing so that the x-axis is coming out of the screen and going into the screen. And so there's the 2 wires with current going in the negative I-hat direction along the negative x-axis into the screen. The 2 wires are a distance a from the origin, and here's our point along the z-axis, which is at 2a. So now what I want you to do is wire 1 is going to have a vector b1, and I want you to draw that in the correct orientation. And then wire 2 is going to have a magnetic field vector b2 at that point along the z-axis. So see if you can draw those 2 vectors. So the 2 vectors are going to be the same length, right, because they're the same distance from the wire, and it's the same current. And the way to get it is to draw this line connecting the wire and the point and the field has to be perpendicular to that line. So that would be B1. And then perpendicular to this line would be B2. But what we need is so you can see these two vectors, their y components are going to cancel and their x components are going to add. And this angle theta is going to be equal. But if this is angle A, this is angle B, well, call it alpha because I already have an A, alpha and beta. What is theta? See if you can figure that out, and then I'll show you. Okay, I'll show you two ways. So notice that this vector B1 is perpendicular to this hypotenuse, right? So that's 90 degrees. So if this is beta, this angle here has to be alpha, right? Because beta plus alpha equals 90 degrees, because it's a right complementary angles in a right triangle. And if this line here and this, the y-axis and the z-axis are perpendicular, and this is alpha, then theta has to be equal to beta. Notice that this is A and this is 2A. So alpha is the inverse tan of 2A. If you want a number, that's 63.4. And beta is the inverse tan of 1/2, and that's 26.6. That's rounded a little bit. So if this is 26.6 and this is 90, that has to be the 63. And if this is 90, that has to be the 26 point, it's actually 565, I think, degrees. But another way of getting it is beta, the cosine of beta is going to be the adjacent side 2A over the hypotenuse, square root of 5A. Whoops. So the cosine of beta, which is how we're going to get those components, right? That's why we need it, is 2 over the square root of 5. So we actually have it without even finding an angle. So what do we have? Let's do B1. B1 equals mu naught I over 2 pi square root of 5a. Oh, did I go over that? I found that over here, right? Because one side is a, so that's a squared. The other side is 2a, that's 4a squared. When you take the square root, you get the square root of 5a. But then we need the cosine of theta. And the cosine of theta, you can go through it on your own, but I got it. It's 2 over the square root of 5. So it simplifies. The 2's cancel, and the 2 square root of 5's give you 5. So we have 1/5 mu naught I pi a. That's the x component of B1, but it's going to be the same for B2, and so you'll have to multiply by 2 to get the final field vector, and it's in what direction? It's it's along the y-axis, right? The way we've defined it, since the y-axis is the way we've drawn it to the right.